Welcome to KJR SummaryCast, audio summaries of peer-reviewed articles published in the Korean Journal of Radiology. Designed to enhance reader convenience and the overall KJR experience, SummaryCast provides conversational audio overviews for time-constrained listeners and mobile-friendly learning. This recording was created using a combination of AI tools with oversight from the KJR editorial team or the article's authors, including necessary edits and corrections. For the most accurate and complete information, we encourage you to also read the original published article.
Welcome to SummaryCast. In the last couple of years, it feels like we've seen an absolute flood of papers testing large language models on every imaginable task in medicine.
It's an explosion, but with that speed comes a problem. A lot of the research is, messy. It's hard to compare studies or even know if a reported result is real because the methods are so poorly described.
Inconsistent reporting. Exactly. It's a huge barrier to actually making progress. How can you build on someone's work if you can't figure out precisely what they did? To address that, we're looking at a new guideline today.
What's the paper?
It's titled Minimum Reporting Items for Clear Evaluation of Accuracy Reports of Large Language Models in Healthcare, 2025 Updates. It was published in the Korean Journal of Radiology in 2025.
MICLEARLLM. That is a mouthful of an acronym.
Actually, look closer. I think they want you to say it as Am I Clear? LLM?
Oh, am I clear? LLM. I see what they did there. That is actually pretty clever.
Right? It sets the tone perfectly. The whole point is clarity.
I like it. So this Am I Clear? LLM is a checklist to try and clean up the reporting chaos.
That's the goal, and it's an update, which is important. The original version focused mostly on the kind of LLMs we first saw, accessed through public web chatbots like ChatGPT.
Right, which was how most of the early studies were done.
But the landscape has shifted, and fast. Researchers are now using more sophisticated methods like application programming interfaces, or APIs, and even deploying their own open-source models locally.
So this update expands the guideline to cover that entire spectrum.
It does. It's trying to keep pace with the technology.
Makes sense. Where does it start? What's the first thing a study needs to get right?
The very first category on the checklist is model identification. It sounds almost too basic to mention, but the paper argues it's one of the most common points of failure.
What does that mean in practice? Just naming the model?
It's more than that. Of course, you need the model name, like GPT-4o or Llama 3.2, and the developer, but critically, you need the version, and ideally, the minor version details.
Why the obsession with minor versions?
Because proprietary models are constantly being updated in the background. The authors give an example. An interface just labeled GPT-4o could be running any number of specific minor versions, which they call snapshots.
So the model you use on Tuesday might be subtly different from the one you use on Friday, even if the name on the box is the same.
Precisely. And that can affect performance. To mitigate this, the checklist says for proprietary models, you must report the exact date of access and query execution. It timestamps your experiment.
Okay, that makes sense for closed source models where you don't have visibility. What about the open source ones where you have the code?
For those, the reporting standard is even higher. It starts with the basics, like the source of the model weights.
You mean whether they're from the official repository or some third-party fork?
Exactly. And then, any modifications you made. Critically, for ultimate reproducibility, you need to report the specific commit hash or release tag.
That's a level of detail you'd expect from a software engineering project, not always a clinical paper.
But that's the point. The paper argues evaluating these models is a software engineering project. It even encourages authors to share the exact model they used in a public repository with a URL link.
Nice idea, but probably a heavy lift for many research teams. One last thing on identification, the cutoff date of training data. Why is that important?
It tells you the scope of the model's knowledge. If a model's training data cuts off in December 2023, it won't know about any medical guidelines or discoveries published after that.
It defines the boundaries of what the model can possibly know.
You got it. So first you have to pin down exactly what model you're testing. What's next?
Let's move on. After identification is what?
Next is model access mode. This is about how you interacted with the model, and it's a major fork in the road for any study's methodology.
The paper lays out three main paths, right? The web chatbot, the API, and local deployment.
Exactly, and they have profoundly different implications for the quality of the research. The web-based chatbot is the easiest to use, which is why it was popular in early studies.
But it's a black box. The paper mentions these opaque system-level features. What are those?
Things like intercession memory, where the chatbot remembers your previous conversations, or hidden system prompts designed to personalize the experience.
And those features can change without warning, which undermines reproducibility.
It's a red flag for a scientific experiment. A key issue is contextual memory within a single session. The model's answer to question 5 is influenced by the first 4 questions and answers.
So unless your research task is specifically about sequential dialogue, this contaminates the results.
That's right. The paper argues that for testing standalone questions, API access is much more appropriate. Each query is treated as a separate, independent call.
It's a cleaner, more controlled experiment. And the third option was self-managed local deployment.
Right. This is where researchers deploy the model, typically an open source one, on their own servers. It offers maximum transparency and control.
And critically, data privacy. If you're working with sensitive patient data, you can't send it to an external server.
A huge advantage, but the trade-off is complexity and cost. The paper gives an example of running a large vision model, Llama 3.2-90B Vision, which required 3 80-gigabyte NVIDIA A100 GPUs.
That is a non-trivial amount of hardware. So the checklist asks researchers to report these computational details?
Yes, for local deployment, you need to describe the hardware environment. It's not just for reproducibility. It provides crucial evidence about the practical feasibility of deploying such a model in a real clinical setting.
Okay, so we've identified the model and how we accessed it. What about modifying its behavior? The paper talks about adaptation strategy.
This is a really important section because the terminology is often used loosely and incorrectly. The authors draw a sharp line between 2 fundamentally different types of adaptation.
What are the 2 types?
The first is parametric adaptation. This is when you actually modify the model's internal parameters, its weights. The most common way is through fine-tuning, where you continue training the model on a domain-specific dataset.
So it's a permanent change to the model itself. The fine-tuned model is a new entity.
Exactly. The second type is non-parametric adaptation. Here, you don't alter the model's weights at all. Instead, you're changing how you interact with it.
Give me some examples.
The most common is prompt optimization or prompt engineering. Another is retrieval augmented generation, RAG, where you provide the model with external documents to use as context.
So the core model remains unchanged, and the problem is that researchers often confuse these two.
That's the key issue. People will use the term fine-tuning or training to describe what was really just clever prompt engineering. The paper argues for precision.
So be specific. If you didn't change the model's weights, don't say you trained it.
You nailed it. And this leads directly to the next checklist category, prompt optimization procedures.
Right. If prompting is one of the main ways to adapt a model, you need to describe it in detail. The paper mentions prompt brittleness. What does that refer to?
It's the phenomenon where very small, seemingly insignificant changes in the prompt wording can lead to dramatically different outputs from the model.
That sounds fragile.
It can be. The paper cites an example where an LLM was asked to classify liver observations. They found that phrasing the task as calculate the LIRADS category versus determine the LIRADS category made the difference between a correct and an incorrect answer.
Wow, just one word.
One word. That's why the checklist insists on thorough documentation. Authors need to explain the rationale for their specific wording, for example, if it aligns with the clinical guideline.
And it's not just about single words. What about broader prompting strategies?
The paper calls those out too. Things like chain of thought prompting or few-shot prompting, where you provide examples. Any of these deliberate strategies need to be explicitly described.
Given this brittleness, how can anyone else hope to replicate the results?
The checklist provides a clear standard. Authors must provide the full, exact, copy-paste-ready text of their representative prompts, not a summary, the exact string.
That's a high bar for transparency, but it seems necessary.
It is. And ideally, researchers should provide a complete record of all the prompts used as supplementary material. They're also encouraged to summarize the optimization process itself. How many versions of a prompt did they try?
It shows the work. Okay, so we have the prompt. The next step is actually sending it. The checklist has a category called prompt execution setup. What does that cover?
This is about the specifics of the query submission. If you used a chatbot, did you enter all questions in a single conversation or start a new chat for each one?
Right, the contextual memory issue.
And for API-based use, it's a similar question. Were the queries independent calls or constructed as a dialogue? All these details affect reproducibility.
So you have to describe the entire experimental script, essentially.
That's the gold standard, yes. Providing the script transparently conveys not just the prompt text, but all of the execution-specific settings, like the exact model version and any other parameters used.
Speaking of parameters, this brings us to one of the trickiest aspects of LLMs, their randomness. The next item is stochasticity management.
This is a subtle but hugely important point. Unlike a traditional AI model that's deterministic, an LLM can generate different responses even when prompted repeatedly with the exact same input.
And this is known as stochasticity. Where does it come from?
It's inherent to how they work. When an LLM generates text, it's predicting the next word based on probabilities. Instead of always picking the single most probable word, it introduces a degree of randomness.
So it might pick the second or third most likely word sometimes, leading to variation in the output.
Precisely. And this randomness can be tuned. The key parameter is called temperature. A temperature of 0 makes the model almost completely deterministic.
While higher temperatures increase the randomness.
Correct. So the first thing a study needs to report is the temperature setting they used. Then, the next question is, how many times did you query the model for each test case?
And if you did it multiple times, how did you synthesize those different responses into a single answer for your analysis?
That's the critical part, and the paper lists several common methods. For instance, did you just need one correct answer across all attempts to count it as a success?
Or did you only use the very first response and ignore the rest?
Right, or maybe you took a majority vote. Each of those methods could give you a different final accuracy score.
A very different score.
So the checklist requires researchers to not only state their method, but also provide the rationale. And they should analyze the consistency of the responses across attempts, which measures reliability.
Okay, this is a big one. It feels like this might be one of the most underreported elements in current studies.
I think that's fair to say, and it connects directly to the final category on the checklist.
The classic problem of data leakage. Is the model cheating by looking at the answers ahead of time?
Exactly. It's a cornerstone of any machine learning evaluation, but it has some new twists with LLMs. The first risk is overlap between the data used to develop the prompts and the data used for the final test.
So if you used a set of 20 cases to develop your prompts, you cannot then include those same 20 cases in your final test set.
Correct. That's direct data leakage. But the paper also points to a more subtle, indirect form. If the researchers crafting the prompts aren't blinded to the test set, they might inadvertently overfit the prompts to that data.
Even if they don't use the exact same cases.
But the really new and massive challenge with LLMs is contamination from the model's original training data.
You mean the fact that these models have been trained on a huge portion of the public internet?
Yes. So if your test data set is sourced from somewhere public online, say questions from a medical journal's website, there's a real risk the model has already seen that exact data during its initial training.
In which case its performance isn't a measure of its reasoning ability, but its ability to regurgitate something it memorized.
Precisely. It's an unintentional data leak. The checklist states that if test data is sourced from the internet, the study must report the exact origins, including URLs, and discuss this potential contamination.
That's a tough problem to solve completely, but acknowledging and reporting the risk is the first step.
It is. It's about being transparent about the limitations of your evaluation.
So let's zoom out. We've walked through the whole checklist. What's the bottom line message here? Is this just creating more work for researchers?
I think the author's perspective would be that this isn't more work, this is the work. Without this level of methodological detail, a study's results are floating in a void. They're not verifiable or reproducible.
It's about establishing a baseline for scientific hygiene in this new field.
That's a great way to put it. It provides a common language and a common set of expectations. For reviewers, it gives them a concrete framework to assess the quality of a manuscript.
And for readers, say a radiologist trying to decide if a new LLM-based tool described in a paper is worth paying attention to.
For them, it's a critical appraisal toolkit. They can go through the checklist and ask, do I know which exact model was used? Was the randomness managed in a reasonable way? Is there a risk the test data was leaked?
It shifts the conversation from a simple headline number, model gets 95% on exam, to a much more nuanced understanding of the evidence behind that number.
You nailed it. It encourages us to move from being impressed by the what to scrutinizing the how. In a field moving this quickly, that critical scrutiny is essential.
So the core takeaway is that for LLM research to be taken seriously as a science, the reporting has to be as rigorous as the engineering. The details aren't just details, they're the entire foundation of the study's claims.
Well said. Am I Clear LLM is essentially a blueprint for building that foundation, ensuring the evidence we generate is sound, transparent, and ultimately useful. And that's all the time we have for this edition of SummaryCast.
Thanks for tuning in.